Our universe is constantly expanding, a reality that makes it extraordinarily difficult to define its limits or to measure its true size. Yet with the advent of the James Webb Space Telescope, JWST, humanity has gained an unprecedented window into the most remote and ancient corners of the cosmos. Since JWST began its mission, it has helped scientists, including well-known figures like Brian Cox, reveal dimensions of the universe that are almost unimaginable to our minds. Within just the fragment of the universe we can observe, astronomers estimate there are around 2 trillion galaxies. This staggering figure is based on detailed studies of the local universe. But even so, we understand that what we see is only a tiny fraction of what could be an even larger, possibly infinite cosmos that lies beyond our observational reach. We are not separate from this universe but an intrinsic part of it. In a profound sense, we are the means through which the universe is able to know itself, to turn its gaze inward and reflect on its own vastness. Thanks to the James Webb Space Telescope, we are embarking on an incredible journey to discover more about the true size of our universe. To put things in perspective, consider travel times in our own solar system. If you were driving a car at a modest 70 miles per hour, you could circle Earth's equator in about 15 days. It would take you roughly 5 months to reach the Moon at that speed, 63 years to get to Mars at its closest point, and an astonishing 4,400 years to reach Neptune. Even these daunting travel times pale in comparison to the actual distances involved in space. For example, the Voyager 1 probe, which launched in 1977 and traveled at about 38,000 miles per hour, did not leave our solar system until 2012. That means it took 35 years just to break free of the Sun's gravitational domain, a journey that emphasizes how vast even our local cosmic neighborhood truly is. Light itself, the fastest thing in the universe, capable of circling Earth 7 times in a single second, begins to feel almost slow when you consider the scale of the solar system and beyond. Yet even our vast solar system is minuscule next to the Milky Way galaxy. Our galaxy contains an estimated 300 billion stars, each likely accompanied by its own system of planets, moons, and asteroids. The nearest star system to us, Alpha Centauri, is 4.3 light-years away. This distance means that even traveling at the speed of light, the ultimate cosmic speed limit, it would take over 4 years to get there. At the Voyager probe speed, that same journey would stretch to around 70,000 years, longer than all of recorded human civilization. These distances make clear just how immense the cosmos truly is. Let's consider another example, Velt Rouge, a star located about 640 light-years from Earth. When you look up at Velt Rouge in the night sky, you're actually seeing light that left its surface around 640 years ago, about a century before Columbus's voyage to the Americas. That ancient light has spent more than 6 centuries crossing the gulf of interstellar space to finally reach your eyes. It's breathtaking to realize that even this star, only 640 light-years away, is considered relatively close on the cosmic scale. Adding to the sense of scale is the concept of the radiosphere, the region of space that our radio transmissions have reached in the past century or so. Even though these signals have significantly degraded, they have nonetheless traveled roughly 100 light-years in all directions, encompassing around 15,000 star systems. This number might sound impressive, but it is still just a sliver of the Milky Way's total population of 300 billion stars. Our radio bubble is tiny, a fragile whisper in the grand expanse of the galaxy. To imagine our cosmic insignificance, think about this. If we shrank our entire solar system down to the size of a US quarter, the Milky Way would be about the size of the entire Earth. Within this enormous structure, with its hundreds of billions of star systems, our own Sun is just one ordinary star among hundreds of billions. And beyond the Milky Way lie at least 1 trillion other galaxies, each with hundreds of billions of stars of their own. 1 trillion is such an enormous number it can be hard to comprehend. Imagine trying to count 1 million cats. Now imagine there are 1,000 groups of those million cats each. That's 1 billion cats. To get to 1 trillion, you need 1 million groups of 1 million cats. The mind almost refuses to grasp it. Yet this is the kind of number astronomers use to describe the number of galaxies in the universe. Our closest large galactic neighbor is the Andromeda Galaxy, situated about 2.5 million light-years away. Andromeda is approaching us at high speed. When it eventually collides with the Milky Way in several billion years, our night sky will be transformed in spectacular ways. Despite the scale of this collision, the chance of any individual stars from the 2 galaxies actually colliding is vanishingly small, highlighting the incredible amount of empty space that exists between stars. These galactic collisions, though largely starless in terms of direct impacts, can reshape the structure of galaxies and even trigger bursts of star formation. Galaxies are not static, They are dynamic systems, evolving over time through gravity and other forces. Beyond our own galactic neighborhood lies the Local Group, a collection of about 50 galaxies that includes the Milky Way and Andromeda. This Local Group is itself part of a larger structure called the Virgo Cluster, which contains over 1,500 galaxies. The Virgo Cluster, in turn, is just one component of an even larger structure, the Laniakea Supercluster, which holds around 100,000 galaxies. Each of these galaxies contains hundreds of billions of stars and planets, representing only a fragment of the larger cosmic web. Even this astonishing scale is dwarfed when we consider the observable universe as a whole. Astronomers estimate there are around 10 million superclusters like Laniakea, containing uncountable numbers of galaxies, stars, and planets. When we map the universe on these scales, we begin to see patterns. Matter in the universe is not spread evenly. Instead, it is organized into a vast cosmic web of filaments, sheets, and voids. These cosmic filaments are colossal structures, long threads of gas, dust, and dark matter stretching billions of light-years, connecting clusters and superclusters of galaxies like a vast three-dimensional spiderweb. The spaces between these filaments are cosmic voids, vast regions that are comparatively empty, sometimes spanning hundreds of millions of light-years across. These voids appear as immense, dark chasms on our maps of the universe, but even these seemingly empty spaces can give rise to future galaxies and structures over time as gravity acts on the tiniest fluctuations in matter. This large-scale structure, the cosmic web, is a testament to the incredible complexity and interconnectedness of the universe. Within these filaments and clusters, a host of remarkable phenomena occur. Supernovae, the explosive deaths of massive stars, disperse heavy elements like carbon, oxygen, and iron throughout the cosmos, seeding future generations of stars and planetary systems. Black holes, especially the supermassive variety found at the centers of most large galaxies, play a crucial role in regulating star formation and galactic evolution. Their intense gravity can shape entire galactic cores and launch jets of energy that travel thousands of light-years into intergalactic space. Even more exotic are quasars, the incredibly bright centers of young galaxies powered by supermassive black holes feeding on matter. Quasars can outshine entire galaxies and serve as cosmic lighthouses, allowing astronomers to study the universe's early history. Meanwhile, the cosmic microwave background radiation, the faint afterglow of the Big Bang, offers the oldest light we can detect, a baby picture of the universe when it was only 380,000 years old. Yet for all our progress, we must grapple with the knowledge that there is much we may never see. Beyond the observable universe lies an uncharted realm from which light has not had enough time to reach us in the universe's 13.8 billion-year history. Because of cosmic expansion, most of these distant galaxies are receding faster than the speed of light relative to us, meaning their light will never reach us. As a result, vast regions of the universe may forever remain inaccessible to observation, hidden behind an event horizon of space itself. Based on current models, scientists estimate that the entire universe could be at least 250 times larger than the part we can observe, and perhaps even infinite in extent. These staggering possibilities force us to confront profound questions about the nature of reality and our place within it. As beings on a small, rocky planet orbiting an unremarkable star in one of hundreds of billions of galaxies, we are nonetheless capable of contemplating these immense scales and asking the deepest questions about existence. Our quest for understanding is supported by extraordinary tools like the James Webb Space Telescope, which not only peers deep into the early universe but also allows us to analyze the atmospheres of distant exoplanets. Thousands of exoplanets have already been discovered, many located in their stars' habitable zones, where conditions might allow liquid water and possibly life. Some of these planets are rocky and Earth-like, while others are giant gas worlds or icy moons that may harbor subsurface oceans. The sheer number of these worlds suggests that life might not be as rare as we once thought. And yet even as we search for life, we confront even bigger mysteries. Dark matter and dark energy, which together make up around 95% of the universe's total mass energy content, remain largely unexplained. Dark matter exerts gravitational influence but emits no light, helping form galaxies and cosmic structures. Dark energy, even stranger, seems to drive the accelerating expansion of the universe. Neither has been directly detected, leaving them among the deepest mysteries in modern physics. Some physicists go even further, speculating about the possibility of a multiverse, an ensemble of countless universes, each with its own physical laws and properties. These universes could exist beyond our own cosmic horizon, forever inaccessible except through the language of mathematics and theory. Meanwhile, time itself is relative, as shown by Einstein's theories. It slows near massive objects like black holes, bending spacetime in ways that challenge intuition and have been confirmed by experiments. Black holes themselves are not just cosmic vacuum cleaners but engines of extreme physics that help regulate galaxies. At the centers of galaxies, including our own,